Welcome to the last section of this discussion. Here we will understand how data is stored in quantum computers leveraging the bizarre behavior of quantum particles. Next, we look at different types of quantum hardware and how the quantum data storage concepts are implemented in each of these modalities. Thereafter, we will discuss the advantages of quantum computers over their classical counterpart, the challenges faced by quantum computers, and how they could team up with classical computers. The concept of quantum computers was proposed by physicist Richard Feynman and mathematician Yuri Manin in the early 1980s. They realized that quantum phenomenon could be efficiently simulated if we could build computers that harness the principles of quantum mechanics. As we discussed in the physics section, at quantum level, the particles behave in a very different and strange way as compared to our macroscopic world. And quantum mechanics is a field that allows for fundamentally different type of computation leveraging this behavior. Using classical computing, it is computationally expensive or infeasible to simulate quantum phenomena. For example, simulating the structure, orientation of molecules in chemical bond, or position of electrons in an atom, it's hard to simulate on classical computing because there are millions of possible configurations. Say, simulating the position of electron in an atom, even if the electrons in the atom were restricted to one of 50 possible combinations within the atom, we would have 2 power of 50 possible configurations. Molecules could be simulated, analyzed to understand their behavior, properties, and interaction with other molecules. And it's an important step in drug discovery. Quantum particles can exist in superposition, have the ability to entangle and influence the state of other quantum particles. Quantum particles can tunnel through barriers that they would not be able to cross in classical systems. We use quantum particles to store information in quantum computers and leverage these phenomena for storage, computation, and communication over network. Like we have bits in classical computers, in quantum computers, the smallest piece of information is called qubit. In the physics section, we looked at how electron spin can be in multiple states at once. Likewise, there are other quantum systems that can exist in superposition of states. In classical computers, a bit can be a 0 or 1, whereas in quantum computers, each qubit can be a 0, 1, or a superposition of both. The superposition could be manipulated and controlled in such a manner that there can be equal probability of getting the qubit to collapse to 0 or 1 on measurement, or varying degrees of probability of obtaining either of the states. This simulation by quantummadesimple.com showcases the superpositions of quantum systems. The histogram showcases the outcome of multiple measurements of a qubit in superposition. You need only 3 qubits to store 8 states, and you could create quantum circuits using Python code to create a superposition of the 8 possible states. Behind the scene, the code is converted to electronic signals that physically control and manipulate the qubits. Qubits can become entangled, meaning their states are correlated in a way that is not possible in classical systems. If you measure the state of one of the particles, then you automatically know the state of the other. There is no theoretical limit to the distance between the particles. If the entangled qubits were prepared in a state of superposition, measuring the state of one of the qubits would collapse the superposition of both. Quantum cryptography is one of the most promising applications of quantum entanglement. By using entangled particles to transmit information, it is possible to detect any attempt to eavesdrop on the communication, as any measurement of the entangled particles will disturb their state, alerting the sender and receiver to the presence of an intruder. Scientists have been successful in creating quantum entanglement using different methods, and this is an active area of research. For example, special crystals can be used to create pairs of entangled photons. The crystal is hit with laser light, and high energy photons are converted by the crystal into 2 photons of lower energy. This allows large number of entangled photon pairs to be produced quickly and easily. Entangling atoms, however, is much more difficult. Individual atoms can be entangled using complicated laser operations. A cloud of ultra-cold atoms is created and held in place by electromagnetic forces on a tiny chip. These atoms are then manipulated so that they do not end up in the state with lowest possible energy, but they are in a state of higher energy. The electromagnetic trap is constructed in such a way that this return to the ground state is physically impossible for a single atom. The atoms can therefore only get transferred to the ground state as pairs and fly away in opposite directions. This creates twin atoms that move exactly in the direction specified by the geometry of the electromagnetic trap on the chip. There are different ways of constructing a qubit. We will discuss few of the popular modalities: superconducting circuit qubit, trapped ion qubit, photonic, and neutral atom qubit. This is a picture of the IBM quantum computer. IBM uses superconducting circuit to create qubits. There are few other modalities of quantum hardware which employ different ways of creating qubits, such as using ions, photons, and neutral atoms, as we already spoke about. In the trapped ion topology, charged atoms, also known as ions, are used as qubit. The ion is trapped in a 3D space using oscillating electric field from radio frequency waves and static electric field generated by electrodes. The ion could be in different possible energy levels due to various contributors like motion of the ion itself or factors such as electron within the ion in high energy orbitals. For storing a qubit, 2 of these energy levels are used as 0 and 1. Measurement and any manipulation of the ion energy level is done using lasers. To initialize the qubit as 0, lasers are used to cool down the ion so as to bring it to a motional ground state, and then specialized lasers are used to get the ion to electronic ground state. When we measure using a laser, the excited state releases a photon and decays to ground state. This photon is detected using photon detectors, and this is measured as 1. The ground state electron will not emit a photon, it is measured as 0. For entanglement, multiple ions are trapped together and they are in a potential well while they are pushing each other apart due to Coulomb's force and the potential well pushing them together. This creates a shared motion of the ions. These are few of the leading players in trapped ion quantum computing. In the case of a qubit created from a superconducting circuit, an inductor-capacitor circuit is used to create an artificial atom such that the energy level of the LC oscillator can be controlled using microwave pulses. We discussed the LC oscillator in the physics section already. The spacing between the energy levels need to be non-linear to replicate an atom. Hence, a special device known as Josephson junction is used as a non-linear inductor. Josephson junction works on the principle of quantum tunneling. It is made of a pair of superconducting aluminum electrodes that are separated by a very thin insulator that is 1,000th of a hair thick. Superconductivity is just a property of materials where materials exhibit zero resistance to electrons flowing in one direction when the material is cooled to a temperature below critical temperature. Aluminium, which is used here, has a critical temperature of 1.2 Kelvin. The superconducting state, achieved at near absolute zero temperatures, allows a resistance-free oscillation back and forth around the circuit loop. Two of the energy levels of this artificial atom are used as 0 and 1, and microwave pulses are used for controlling the transition between these energy levels. These are the leading companies in the superconducting circuit quantum computing. In the photonic quantum computer, photons are used to store information. The hardware is capable of emitting and detecting single photons. There are pathways for photons to travel inside the photonic processor. Beam splitters and phase shifters are used for creating the quantum states. Phase refers to the relative timing of different waves, which can also be used to encode information. Phase shifting of photons is achieved by modulating the temperature of the medium through which the photons are traveling. When the temperature is changed, the speed with which the photons travel in the medium changes. Another way to encode information in photonic qubits is to use polarization. Polarization refers to the orientation of the electric field of a photon, which can be manipulated to represent information in a quantum computer. Say horizontal polarization could be a 0 and a vertical polarization a 1. A photon, for example, can be in a superposition of horizontally polarized state and a vertically polarized state until it passes through a polarimeter. Polarimeter are analytical hardware components for measuring the polarization of light. For measurement, photons are converted to electricity using photodiodes. And the best part is, photonic computers do not require ultra-cold temperatures. These are the leading companies in photonic quantum computing. The neutral atom approach uses optical tweezers to hold an array of atoms in a palm-sized vacuum chamber. Alkaline earth element atoms are trapped and cooled by lasers and then arranged a few microns apart from each other. They are made into qubits by precisely controlling the spin of each atom's nucleus and entanglement between their electron clouds using pulses of light. The atoms are so close to each other that millions of them can feasibly be held in the same small vacuum chamber without significant growth of the overall system footprint. Quantum advantage refers to the potential ability of quantum computers to solve certain problems much faster than classical computers. It is important to note that not all computational problems can be solved faster by a quantum computer than a classical computer, and it is still an active area of research to determine which problems are suitable for quantum algorithms. Quantum parallelism is a fundamental concept in quantum computing that allows quantum computers to perform multiple computations simultaneously. Using quantum superposition, it is possible to apply a function to all possible states of the n qubits at once. Quantum algorithms use this phenomenon to solve optimization problems, computations like finding the factors of large numbers, or searching for an item in an unstructured database, so on and so forth. An example of optimization problem is optimizing the car design for maximizing interior space and finding the best aerodynamics out of all the possible options. This is one of the use cases BMW is already working on. Two of the most popular quantum algorithms are Grover's algorithm and Shor's algorithm. Grover's algorithm is a quantum search algorithm that allows searching for an item in an unstructured database as compared to its classical counterpart of performing linear search over unstructured data. It provides quadratic speedup. The algorithm utilizes quantum parallelism as one of the steps in the search. Let's say if we were to search for an item X out of 8 items, could be anything, say 8 numbers, we will need 3 qubits to store this information, and we will map the classical data to 8 possible states of these 3 qubits. Assuming we are able to define the search requirement as a function or constraint such that we need to find an item X that satisfies this constraint. The way the quantum algorithm works is, first, all possible 8 states are put in equal superposition. One of these is the item we are looking for. The algorithm thereafter applies a black box function to all possible states and is able to mark the state that satisfies the function. But we can't measure yet, as the measurement can produce any of the 8 possible states as outcome with equal probability. Next, a few steps are executed iteratively to increase the probability of this marked state, which is the solution, and reduce the probability of all other states. If there are n items to search from, then the maximum iterations that are required to increase the probability of correct answer is only square root of n. Hence the quadratic speedup over classical unsorted linear search algorithm. Public key cryptography is the field of cryptography that uses pair of keys, public key and a private key. Public key can be openly distributed without any compromise to security, whereas private key is confidential. Anyone with a public key can encrypt a message, yielding a ciphertext, but only the person who has the private key will be able to decrypt the ciphertext to obtain the original message. RSA is one of the oldest and widely used public key cryptosystem algorithm for securing data transmission. RSA uses two large prime numbers to construct the public key and the private key. The public key is a product of these two numbers, and the private key is also a function of these two numbers. The security of the algorithm relies on the fact that factorizing the public key is computationally not feasible using the classical computers we have today, and thus the private key is safe. Classical computer would take 2 power of n operations to factorize a number that can be represented in n number of bits. This exponential complexity of execution time is reduced by utilizing quantum, and on quantum computers it can be done in a polynomial complexity. Again, quantum parallelism facilitates this speedup. Shor's quantum algorithm allows for factoring these large RSA public keys and thus obtaining the private key using the public key. A quantum computer with around 4,000 error-free qubits could defeat RSA in seconds. We currently have 400 qubit plus quantum processors and IBM and Google already have roadmaps to achieve 1 million by 2030. This introduces us to the need for preparing ourselves from quantum hacking, which poses a huge threat to all the data that we now consider secure, in the event that encryption algorithm be cracked later using quantum computers. Organizations will have to start preparing now for the migration to quantum safe cryptography by cataloging where and how cryptography has been used within the organization, impact analysis of encryption break, and identifying high value assets. PQC refers to the development of cryptographic algorithms that are resistant to attacks from both classical and quantum computers. The primary goal of PQC is to replace current public key cryptographic systems that will be broken by large-scale quantum computers with secure alternatives. PQC algorithms are designed to be resistant to Shor's algorithm. In classical computing, data and keys are sent as classical bits, zeros and ones, as stream of electrical or optical pulses. It is possible for miscreants to read and copy these bits during transit without leaving a trace. Quantum communication takes advantage of quantum behavior. In quantum communication channel, each qubit could be transmitted as a photon in superposition along optical cables. If a hacker tries to observe or copy these qubits in transit, the superposition collapses to either 1 or 0, thus leaving behind a sign of activity. The quantum key distribution protocol works on this principle. The encryption key is transmitted over a quantum channel, and if any intrusion is identified, the key is regenerated and sent again until a secure key transmission has been achieved. The data could now be encrypted, decrypted using this key, and can travel as classical bits over classical channel. We still have challenges to overcome though. Once universal quantum computers are available, the possibility of someone being able to break encryption key would have to be considered. Using the above method, we are still sending the message over classical channel, which means it can be copied and it is prone to malicious activity. The solution is to use quantum channel for the entire data transaction. In this case, data transmission will be done using entangled photon pairs, where one of each pair of entangled photons is with the sender and receiver respectively. Any changes done by the sender to the photons on their end will change the state of the photons of the recipient. This process is called teleportation. The other challenge is that qubits are fragile. Few of the qubits in transit might lose their quantum state. Also, the material in optic cables could absorb few photons. This poses a limit to the distance quantum information can travel without corruption. The solution that is used now to deal with this situation is to have stations in the path that will decrypt the quantum information as classical bits and then re-encrypt in a fresh quantum state for their journey to the next node. This technique again poses a threat to the stations being attacked and the decrypted information from the station being copied by intruders. What we require is quantum repeaters that is capable of amplifying the quantum signal, retaining the original quantum state. Another open question is what makes quantum entanglement work is still something we don't completely understand. Once we figure out the underlying science behind it, would that make entanglement vulnerable to quantum attacks too? That's a question we might have to deal with in future, but for now, quantum communication looks quite secure and has gathered a lot of interest from big firms. Quantum computers are a promising technology, but they also face several challenges that need to be overcome before they can become practical for a wide range of applications. Some of the major challenges include the hardware being complex, bulky, and expensive to build, as it requires use of ultra-pure materials, and engineering design that ensures strictly no interference from environment, as that can disturb the qubit states. Most topologies require maintaining extremely low temperatures. Qubits are highly sensitive to their environment, and the slightest external disturbance, including heat, vibration, and electromagnetic radiation, will destroy the quantum states. Quantum computers are prone to errors due to the fragile nature of qubits. Noise increases with qubit count, requiring complex error correction approaches. Building reliable quantum computers with million plus qubits along with the software and algorithm to provide valuable computation is the future goal. We have a 433 qubit computer by IBM today. Furthermore, we require more quantum algorithms, software frameworks for quantum computers, and development of standards to ensure interoperability between different quantum computing platforms. While research and development of a universal quantum computer is underway, and having a full-fledged quantum computer is a distant goal, a quantum classical hybrid computing approach can combine the power of both classical and quantum computing to solve complex problems. The hybrid approach can involve breaking a complex problem into smaller sub-problems that can be solved using a combination of classical and quantum computing resources. The classical computer can be used to control and interact with the quantum computer, and the software architecture would be designed to enable seamless communication and data flow between the two systems, where the classical computer could perform initial pre-processing of the data and perform post-processing of the results obtained from the quantum computer, while the quantum computer performs the core calculations that are difficult for a classical computer to perform. The integration may involve the development of specialized software libraries, APIs, and communication protocols that allow the two systems to work together. The classical computing algorithm will include invoking quantum APIs as and when required. And behind this API layer, the quantum hardware complexity would be masked from the programmer. This API layer could be for a specific quantum hardware implementation provided by that company, or it could be a generic API layer loosely coupled to quantum hardware in such a manner that any changes to the choice of quantum hardware has zero impact on code. This is what happens inside the quantum processor and the hardware gray box. The high-level quantum code is compiled by the quantum processor and then converted to quantum circuits containing details of all the gates that need to be applied to the qubits. And this is done according to the specific quantum hardware on which it will be executed. This involves mapping the logical qubits in the circuit to physical qubits on the hardware, taking into account any limitations or constraints of the device. The compilation process also optimizes the circuit to minimize the number of gates required and reduces the likelihood of errors. Note that, like we have classical gates and or XOR, NOT, etc. in classical computers, there are quantum gates in quantum computers, and at the machine level, these gates need to be applied to qubits to manipulate the quantum states and perform quantum operations. After the circuit is compiled, it is then translated into electronic signals that can be sent to the quantum hardware. These signals are typically in the form of microwave pulses or other forms of electromagnetic radiation that are used to manipulate the qubits and execute the gates defined in the circuit. Again, the signals that are sent to the quantum computer to apply quantum gates depend on the specific technology of the quantum computer. The electronic signals are sent to the quantum hardware through a communication channel such as fiber optic cable or wireless communication. Depending on the quantum hardware architecture, these signals may be manipulating the magnetic properties of qubits such as the spin of electrons, or the energy level of qubits such as the electronic states of atoms, and so on. The measurement of the results from circuit execution are received by the quantum processor through the same communication channel. Before we close the discussion, I would just like to say that it is hard to predict with high accuracy as to when we will have large-scale fault-tolerant quantum computers. The next decade is crucial and could bring about a lot of changes to the world of computing, opening new dimensions to what humans can accomplish. Time to embrace the future and be part of the development is now.